Hi, my name is Pedro Sampaio, and I'm the CEO and co-founder of NeobeTX, where we are engineering live biotherapeutic products to enable immunotherapeutic success in current non-responding cancer patients. Now, we're doing this because even though immunotherapy has changed the clinical landscape of oncology, we're still stuck at a number of about 15 to 20% of patients only that successfully respond to this. Now, to understand why, we like to use this metaphor of tumors as castles and immune cells as an army trying to overtake this castle. And in a subset of tumors, its local microenvironment can create barriers that prevent these immune cells from getting into the tumor and successfully reaching cancer cells in order to do their job. Now, this leads to what is known as immune-excluded tumors, where you can clearly see a tumor-reactive immune reaction being generated, with cancer-reactive immune cells being trapped in these interstitial stromal regions, unable to get close to cancer cells. Now, one of the main mediators of this phenotype is the extracellular matrix, a mesh of local fibers that can both trap immune cells, but also signal into them, preventing their effective activation. Oh, for this reason, targeting the extracellular matrix has become a priority in immuno-oncology, and there have been several strategies in order to attempt this. One strategy is to target the stromal cells that are responsible for producing this extracellular matrix, like fibroblasts and macrophages, through things like TGF-beta inhibitors, for example. Now, the problem with these is that they don't target the extracellular matrix that are already in place, and you also have accessibility constraints to target these cells specifically in the tumor microenvironment. On the other hand, you have the targeting of the extracellular matrix components themselves, like collagens and proteoglycans that we know are involved in immune cell trapping. But strategies to attempt this in the past have relied on the systemic delivery of drugs, which can lead to severe off-target toxicities because these components of the extracellular matrix are common to healthy tissues. There's a clear need for new strategies that allow us to target the extracellular matrix in these tumors directly, improving infiltration into the tumor, but without added toxicities. Now, at Neo, we think that the solution for this is bacteria, and specifically genetically engineered tumor colonizing strains of bacteria, which we are engineering to disrupt the tumor ECM specifically. Now, we're taking strains of bacteria that have been shown to colonize tumors effectively once they are delivered systemically into patients, and we are genetically engineering them with biosensors to be triggered once these bacteria are established in the tumor to produce a payload that targets extracellular matrix components directly. Now, these payloads are secreted into the tumor extracellular space. They take apart these components of the extracellular matrix and enable the infiltration of immune cells, enabling immunotherapeutic efficacy in these patients. Now, how exactly are we targeting these bacteria? We're doing that through a modular approach, engineering independent genetic circuits that will then be put together into our final products. These genetic circuits code for the biosensors, our tumor-inducible promoters that ensure that these bacteria are only activated once they reach the tumor, and the payloads, the enzymes that target specific components of the extracellular matrix that we have identified and that are involved in immune cell trapping. We're introducing a secretion system to make sure that these payloads are released directly into the extracellular space without the need for cell-mediated steps, and an antibiotic-free plasmid stability system to ensure safety and clearance for administration into patients. All of these circuits are being engineered using the basic DNA assembly platform, which is open source and was developed by Jeff Baldwin, who is the co-director of a Center for Synthetic Biology at Imperial College and one of the advisors of Neo. We've already used this to generate an extensive library of genetic circuits covering these modules, which will form the backbone of our bacterial engineering platform, which we're looking to protect later this year. Using this strategy, we've already been busy building our initial prototype using strains of bacteria that have been previously demonstrated to effectively colonize tumors, in which we have already engineered to produce a payload, to be induced to produce a payload that's effectively degrades extracellular matrix components involved in immune exclusion. And we're now taking these bacteria into patient-derived decellularized explant tissues that maintain the exact same extracellular matrix architecture that is seen in patients. And you can clearly see our bacteria in green here infiltrating these tissues over time. Now, we're currently taking these bacteria into efficacy studies using both these models and hopefully tumor-bearing mouse models in the future. We think we've got the right team in order to be able to achieve this. I've been working in the tumor microenvironment for over 13 years in top academic institutions, and my co-founder Annalise has several years of bacterial engineering for different therapeutic indications. We've got a world-class panel of advisors spanning both immuno-oncology and bacterial engineering and business support from Deep Science Ventures and Cancer Research UK. If you'd like to find out more, please contact us by email or on LinkedIn, find us or on our booth during the conference on the 7th. Thank you very much.